Okay, a very good afternoon to you all present here. Today is the second day of our Geotech Asia, and we were thrilled to welcome each one of you here. And I would like to invite our thematic speaker, Dr. C.R. Parthasarathi. He is a founder, chairman, and managing director of the Tharthi Geotech Engineering Services, Bangalore, Urban, Karnataka, India. He holds his BE and ME from Bangalore University, PhD from IISc Bangalore, with nearly 30 years of geotechnical experience in site characterization, deep foundation, testing, and consulting in India and abroad for large-scale projects. He has achieved expert level in the PDI or PDCA proficiency tests on dynamic measurement and analysis USA. So now I'll hand over to Dr. Parthasarathi.
Thank you, Ms. Charity, for an elaborate introduction. Thank you, Chairman. Good afternoon, namaskar to all of you. At the outset, I thank the organizers for inviting me and giving me an opportunity to speak on today's topic, the carbonate content, how is it important and how does it impact on the geotechnical designs. With my co-author, Dr. Prashant Talkad, and some of the work and many of such kinds have been handled by our team here, Ashita and Sumant, Sangeeta as well. Friends, carbonate soils is one of the most problematic soil and poses challenge for geotechnical engineers. It reminds me, before I started my career in 2001 in offshore geotechnical engineering, expansive clays is equally a challenging problem for geotechnical engineers, and it's a global problem. So likewise, the carbonate soils are also challenging, and it's a global problem. So I manage large-scale investigations across the geographies on various vessels with different contractors. What I found is these carbonate sediments exist across the world. In Australia, I could see north and west. In India, east coast and west coast is predominant. Philippines, Indonesia, Vietnam, Middle East, etc. What is the difference between the silicate material and the carbonate material? The silicate has the quartz grains where the mechanical properties are very well defined. The carbonate materials are biogenic in nature, and these are the skeletal remains of the corals, the shells, and the marine organisms. And you have very unpredictable parameters, properties of the carbonate soils because of the calcium content in it. It has a high void ratio. The pore structures are very flowable. It undergoes large compression because under low stress levels the interparticle process breaks, and those grains, because it's biogenic in origin, it undergoes crushing due to loadings, and therefore particle crushing induces the softness, and thus for the design of piles you have a very low limiting skin friction. The framework for classifying the carbonate soils is Clark and Walker is a geotechnique publication. You could see the cemented material, uncemented material, and cementation. I draw your attention to this to classify the carbonate sand. A carbonate content more than 90% is treated as carbonate sand, and less than 10% is treated as silica, and anything in between is calcareous, and you'll have to do an interpretation of the parameters. So I pulled out this from Phil Watson, who is the chair of TC209 of offshore. He presented in one of his paper, and look at the CPT data. You have the refusal to cone resistance, and you have the carbonate sand and carbonate silt, cemented layers, and with different water depths in the same region, the data appears not to be superimposing on each other, that tell us on the heterogeneity of the material itself. Since this undergoes large compression, you see the volume change for this bioclastic or biogenic materials. See high void ratio changes, where the similar relative density, the silicate materials, doesn't undergo much of compression. So Arjima, the Clarom publications brought out some guidelines to how to characterize the carbonate materials. Before I talk about it, it reminds me to recall the literatures where the problem existed in the early 80s on North Rankin A platform in Australia. The Woodside engineers, they were monitoring the driving of piles 2 meter diameter, 125 meter below the seabed. They found that the driving resistance was very low and the unit skin friction was not going to be achieved for the intended capacity. So then they commissioned the research group under the guidance of engineer Graham Prince with a Commonwealth Scientific Industrial Research Program. They studied the micro behavior, mechanical behavior, and then formed the guidelines. There are several conferences, at least two, one in Australia in the late 80s and one in Bahrain in 1999. And then this industrial research program, Arjima Clarum, has published, which gives you the guidelines of how to handle the carbonate and characterize them. So one such characterization requirement is to perform a compression test, the odometer test. Either you can do an isotropic compression in triaxial or perform an odometer test and develop this tangent. The slope of this at 800 kilopascal is defined as the limit compressibility index. And there are some researchers who also have shown to use the secant compressibility index, but tangent limit compressibility index at 800 kilopascal is very well received in the industry and still is being practiced. And there some researchers also shown the crushing coefficient. So if you perform a grain size distribution before and after the test, and you could see there's no change in silicate material, but apparently you could see the particle crushing in carbonate phenomenon, and this crushability index is defined here. So if you encounter a crushing coefficient, that means you already realizing that these materials becoming finer, and therefore you'll have to be a little careful in using them for any of your design. So it's also led to how to choose the limiting skin friction and the limiting end bearing, and you could see here 10 to 20 kilopascals and 2 to 4 megapascals on the end bearing and the skin friction respectively. And here is the limit compressibility index, which is the slope of the tangent at 800 kilopascal. There are some researchers who have told, for example, Professor Landorf, that you could also have not 800 but much higher pressures if there is any cemented materials. So this reminds me to pull out one case study which shows that 20 kilopascal shear strength. This is from offshore west coast India. ONGC has done this, and also the limiting end bearing is 2 to 4 megapascals. It is similar framework in the previous slides. It is derived, and the material characterized is sand. So with this low unit skin frictions, you develop the capacities. Obviously, it's very low capacity. You tend to evaluate your initial self weight of those pile foundation. Okay, with no resistance, you obviously expect about 15 to 20 meters of self weight penetrations, and then you develop the soil resistance to driving and the blow counts in the wave equation program, and choose a 900 kilojoules hammer is necessary to drive the piles to 90 meters deep. But however, the self-weight penetration is expected to be around 15 to 24 meters. With this, the piling contractor was very careful that expecting a very deep self-weight penetrations, and they also wanted to put some pile stoppers or retainers so that they don't sacrifice the piles in case the uncertainty exists and piles will be lost. But when actual driving began, the pile did not experience any settlements. It's only about 1 meter. You have a high blow count at the surface, and this actually panicked everybody offshore because it's very expensive. The barge time is consuming, and they don't know what to do. So what happened here, when the pile did not experience settlement, there was a 15 meters of pile length sticking up. When you put the hammer, even with the maximum boom, you are not able to place the hammer on top of the pile. So they were not able to drive unless they put a small hammer. One of the pile, they have to chop it, drive it, and then have to weld it again. It consumed barge time. So we went back and look at, I'm connecting this 20 kilopascal with the cemented nature of the carbonate content, is only 1 meter of self-weight penetration. When you look at the CPT, it gives 35 megapascal of the cone resistance, a refusal stratum. Apparently, when you don't use proper tools and rigs, you are not able to quantify what is the material here. And in this case, there was no drilling or triple tube core barrel used, and therefore they characterized the material as sand. A conservative estimate for pile capacity is fine, but that doesn't suit the drivability and the initial self-weight penetration assessment. This is so simple, but this is one of the very important lessons that we learned in the offshore project. From then onwards, for every subsequent projects, we put it as a process that we make assessment for zero penetration, these stick-up checks, as well as to verify all the data available in quantifying the material so that we don't lose out and be embarrassed on the project. Okay, this is 20 kilopascal and only 1 meter things. I had an opportunity and was honored to work on a project about 20 years back in Australia. This is using the portable remote operated drill that was operated by Benthic Geoscience in Australia. So it has two magazines where all the drill rods, the CPT cones, the core barrels are housed in these two magazines. The entire unit is placed on the seabed, and then the driller is drilling in the computer, collecting samples, pushing the CPT cones, collecting the core samples using triple tube, but you cannot take out the material. It is housed in the magazine, and after certain progress, then they bring the tool out on the deck and they recover the samples, and then you characterize those materials. So because of the topic, I pulled out these old photos from those days, and you see the uncemented material here, and also the cemented materials that you encounter in the borehole. Okay, unless for these kind of materials is so fragile, if you don't use triple tube core barrels, you will not be able to get these kind of core samples. And we face the same problem in our onshore geotechnical investigation in characterizing the overburden and the material between overburden and the sheetrock. So one of the ways to characterize this carbonate material.
Okay, a very good afternoon to you all present here. Today is the second day of our Geotech Asia, and we were thrilled to welcome each one of you here. And I would like to invite our thematic speaker, Dr. C.R. Parthasarathi. He is a founder, chairman, and managing director of the Tharthi Geotech Engineering Services, Bangalore, Urban, Karnataka, India. He holds his BE and ME from Bangalore University, PhD from IISc Bangalore, with nearly 30 years of geotechnical experience in site characterization, deep foundation, testing, and consulting in India and abroad for large-scale projects. He has achieved expert level in the PDI or PDCA proficiency tests on dynamic measurement and analysis USA. So now I'll hand over to Dr. Parthasarathi.
Thank you, Ms. Charity, for an elaborate introduction. Thank you, Chairman. Good afternoon, namaskar to all of you. At the outset, I thank the organizers for inviting me and giving me an opportunity to speak on today's topic, the carbonate content, how is it important and how does it impact on the geotechnical designs. With my co-author, Dr. Prashant Talkad, and many of the work, some of the work and many of such kinds have been handled by our team here, Ashita and Sumant, Sangeeta as well. Friends, carbonate soils is one of the most problematic soil and poses challenge for geotechnical engineers. It reminds me, before I started my career in 2001 in offshore geotechnical engineering, expansive clays is equally a challenging problem for geotechnical engineers, and it's a global problem. So likewise, the carbonate soils are also challenging, and it's a global problem. So I manage large-scale investigations across the geographies on various vessels with different contractors. What I found is these carbonate sediments exist across the world. In Australia, I could see north and west. In India, east coast and west coast is predominant. Philippines, Indonesia, Vietnam, Middle East, etc. What is the difference between the silicate material and the carbonate material? The silicate has the quartz grains where the mechanical properties are very well defined. The carbonate materials are biogenic in nature, and these are the skeletal remains of the corals, the shells, and the marine organisms. And you have very unpredictable parameters, properties of the carbonate soils because of the calcium content in it. It has a high void ratio. The pore structures are very flowable. It undergoes large compression because under low stress levels the interparticle process breaks, and those grains, because it's biogenic in origin, it undergoes crushing due to loadings. And therefore, particle crushing induces the softness, and thus for the design of piles, you have a very low limiting skin friction. The framework for classifying the carbonate soils is one Clark and Walker is a geotechnique publication. You could see the cemented material, uncemented material, and cementation. I draw your attention to this to classify the carbonate sand. A carbonate content more than 90% is treated as carbonate sand, and less than 10% is treated as silica, and anything in between is calcareous, and you'll have to do an interpretation of the parameters. So I pulled out this from Phil Watson, who is the chair of TC209 of offshore. He presented in one of his paper, and look at the CPT data. You have the refusal to cone resistance, and you have the carbonate sand and carbonate silt, cemented layers, and with different water depths in the same region, the data appears not to be superimposing on each other, that tell us on the heterogeneity of the material itself. Since this undergoes large compression, you see the volume change for this bioclastic or biogenic materials. See high void ratio changes, where the similar relative density, the silicate materials, doesn't undergo much of compression. So Arjima, the Clarom publications brought out some guidelines to how to characterize the carbonate materials. Before I talk about it, it reminds me to recall the literatures where the problem existed in the early 80s on North Rankin A platform in Australia. The Woodside engineers, they were monitoring the driving of piles 2 meter diameter, 125 meter below the seabed. They found that the driving resistance was very low, and the unit skin friction was not going to be achieved for the intended capacity. So then they commissioned the research group under the guidance of engineer Graham Prince with a Commonwealth Scientific Industrial Research Program. They studied the micro behavior, mechanical behavior, and then formed the guidelines. There are several conferences, at least two, one in Australia in the late 80s and one in Bahrain in 1999. And then this industrial research program, Arjima Clarom, has published, which gives you the guidelines of how to handle the carbonate and characterize them. So one such characterization requirement is to perform a compression test, the odometer test. Either you can do an isotropic compression in triaxial or perform an odometer test and develop this tangent. The slope of this at 800 kilopascal is defined as the limit compressibility index. And there are some researchers who also have shown to use the secant compressibility index, but tangent limit compressibility index at 800 kilopascal is very well received in the industry and still is being practiced. And there some researchers also shown the crushing coefficient. So if you perform a grain size distribution before and after the test, and you could see there's no change in silicate material, but apparently you could see the particle crushing in carbonate phenomenon, and this crushability index is defined here. So if you encounter a crushing coefficient, that means you already realizing that these materials becoming finer, and therefore you'll have to be a little careful in using them for any of your design. So it's also led to how to choose the limiting skin friction and the limiting end bearing, and you could see here 10 to 20 kilopascals and 2 to 4 megapascals on the end bearing and the skin friction respectively. And here is the limit compressibility index, which is the slope of the tangent at 800 kilopascal. There are some researchers who have told, for example, Professor Landorf, that you could also have not 800 but much higher pressures if there is any cemented materials. So this reminds me to pull out one case study which shows that 20 kilopascal shear strength. This is from offshore west coast India. ONGC have done this, and also the limiting end bearing is 2 to 4 megapascals. It is similar framework in the previous slides. It is derived, and the material characterized is sand. So with this low unit skin frictions, you develop the capacities. Obviously, it's very low capacity. You tend to evaluate your initial self weight of those pile foundation. Okay, with no resistance, you obviously expect about 15 to 20 meters of self weight penetrations, and then you develop the soil resistance to driving, and the blow counts in the wave equation program, and choose a 900 kilojoules hammer is necessary to drive the piles to 90 meters deep. But however, the sulfate penetration is expected to be around 15 to 24 meters. With this, the piling contractor was very careful that they expecting a very deep sulfate penetrations, and they also wanted to put some pile stoppers or retainers so that they don't sacrifice the piles in case the uncertainty exists and piles will be lost. But when actual driving began, the pile did not experience any settlements. It's only about 1 meter. You have a high blow count at the surface, and this actually panicked everybody offshore because it's very expensive. The barge time is consuming, and they don't know what to do. So what happened here when the pile did not experience settlement? There was a 15 meters of pile length sticking up. When you put the hammer, even with the maximum boom, you are not able to place the hammer on top of the pile. So they were not able to drive unless they put a small hammer. One of the pile, they have to chop it, drive it, and then have to weld it again. It consumed barge time. So we went back and look at, I'm connecting this 20 kilopascal with the cemented nature of the carbonate content, is only 1 meter of sulfate penetration. When you look at the CPT, it gives 35 megapascal of the cone resistance, a refusal stratum. Apparently, when you don't use proper tools and rigs, you are not able to quantify what is the material here. And in this case, there was no drilling or triple tube core barrel used, and therefore they characterized the material as sand. A conservative estimate for pile capacity is fine, but that doesn't suit the drivability and the initial sulfate penetration assessment. This is so simple, but this is one of the very important lessons that we learned in the offshore project. From then onwards, for every subsequent projects, we put it as a process that we make assessment for zero penetration, these stick-up checks, as well as to verify all the data available in quantifying the material so that we don't lose out and be embarrassed on the project. Okay, this is 20 kilopascal and only 1 meter things. I had an opportunity and was honored to work on the project about 20 years back in Australia. This is using the portable remote operated drill that was operated by Benthic Geoscience in Australia. So it has 2 magazines where all the drill rods, the CPT cones, the core barrels are housed in these 2 magazines. The entire unit is placed on the seabed, and then the driller is drilling in the computer, collecting samples, pushing the CPT cones, collecting the core samples using triple tube, but you cannot take out the material. It is housed in the magazine, and after certain progress, then they bring the tool out on the deck and they recover the samples, and then you characterize those materials. So because of the topic, I pulled out these old photos from those days, and you see the uncemented material here, and also the cemented materials that you encounter in the borehole. Okay, unless for these kind of materials is so fragile, if you don't use triple tube core barrels, you will not be able to get these kind of core samples. And we face the same problem in our onshore geotechnical investigation in characterizing the overburden and the material between overburden and the sheetrock. So one of the ways to characterize these carbonate materials is to qualitatively test with calcium hydrochloric acid, 1 normal hydrochloric acid, whether it is reacting extremely high, moderate reaction, or no reaction. The moment you see there is some reaction, you subject these materials to further carbonate content test as per the ASTM standards, and this carbonate content will dictate what kind of parameters to be chosen for your pile designs. And again, I prepared this 20 years back in 2006, and you could see the cone resistance. You have a high CPT cone resistance, and it refused at 10 meters. These are all uncemented material in the top 10 meters. Suddenly you see a cemented material, well cemented material. This is for an anchor project, and you could see there's only 4 data set. I put there about 11 or 12 in that region, circular locations. None of them are superimposing on each other. Clearly shows the heterogeneity of these carbonate materials vertically as well as laterally. And you see the uncemented material and the cemented material. The strength of these at 10 meters was about 14 megapascals, while at 15 meters was only around 2 megapascals of unconfined compressive strength. So the particle curve itself is moving towards becoming finer. And this is one of the important characterization that we have to assign to do the grain size distribution before testing and after testing, is be it a direct shear test, a consolidation test, an odometer test, or so on. I just illustrate quickly two case studies, one on the cemented layer, the other one is on the uncemented materials. How do we handle the carbonate nature? In this case, it's very prominent in offshore Abu Dhabi. You can see the carbonate content is in excess of about 90%, and the material, I could see the legend is predominantly cemented materials. Only at the surface you could see an uncemented material, while at deeper depths predominantly you have the cemented layers. The unconfined compressive strength varied between 1 to 4 megapascals. So with this kind of predominantly cemented layers, your driven piles is not conducive. So you have to resort to drilled and grouted piles. So what is normally done is they use these primary piles driving this casing until a competent material, so that during the drilling then there is no boreal collapse. And once you drive that, you make a hole and then you insert the pipe and grout it. So the capacity is dictated by the interface between pile and the grout and the rock. And these piles will have the shear keys at a certain spacing and also the thickness, and therefore the capacity is dictated by the unit skin friction based on the unconfined compressive strength, and also it is the pile to grout. You have the grout strength, generally about 35 megapascal is used in this region. And then you estimate the ground model with these previous slides, estimate of the friction and then the capacities. Okay. So you have to drill this. Usually in this drilled and grouted pile, you will not consider the end bearing component, is only the friction component. So what if you don't have a cemented layer? Again, in Saudi Arabia, you can see the carbonate content in excess of 80%. At certain depths, it's between 60 to 70%. So anything more than 80%, you treat this as a carbonate soils. Less than 20%, you treat as a silicate material. And anything between 20 to 80%, you just have to do some interpretation. So here in this case, they do a logarithmic interpolations to get this unit skin friction and end bearing. So wherever it's more than 80%, you limit the skin friction to 20 kilopascal and 3 megapascal on the end bearing, and the other way you interpret between 20 to 80%. Okay. So you develop this capacity, and I want to illustrate here. If you don't consider the carbonate content, you are actually over predicting the pile capacity. If you consider the carbonate content, you will have the realistic value. And we have seen losing pile and losing hammer and so on and so forth. So with these two illustrations, I want to highlight in the regions that I have worked, you could see a normally consolidated profile, all cohesive soils. Okay. And in east coast of India is a under consolidated material with OCR less than 0.5. If you go to Middle East, the minimum shear strength is around 300 kilopascal. Sometimes you get the cemented layers is non-carbonate, we term this as gypsum, and in the carbonate region it's calcarnite, calcilucetate, etc. as per the Karak and Walker table. So therefore, in order to bring different perspective stratigraphy and the response of these materials and the risk that this stratigraphy offers to the installation of offshore oil and gas structures, I have written this book. In compiling my experience and the company's experience in all these 5 geographies, it was inaugurated about a couple of months back on the book cover, and I'm happy to share that this book is published now. Okay. And it's available across the world in Amazon. I'm equally delighted that this book I was happy to present to my research supervisor, Professor K.S. Subbarao. With this, I conclude this. Thank you, Chairman, for this. I acknowledge all these people and acknowledge for all of you. Thank you for patient listening. Thank you.
Yeah, thank you, Dr. Parthasarathy, for maintaining the time. So it was a wonderful lecture. So you can take one question, 1 or 2 questions. Yeah.
Thank you, Dr. Partha. It's very interesting. We've actually found carbonate soils even in onshore. So we were playing around with it, and I found, so we were experimenting. So triple tube is great, HCl is great, The third way which we found is to, at the same site, we did a seismic cone and we did regular CPT. Right? So the ratio between the degraded modulus and the actual modulus you get from CPT correlation, that gives you the extent of cementation. So that there's a Robertson 2016 actually talks about it. So aging factor you can calculate from shear wave velocity measurements. I think it's faster than triple tube, especially offshore.
No, offshore you cannot use always unless you have the core sample because the insurance guidelines doesn't permit. So we'll have to supplement some of those direct testing
Correct.
with the
I
actual.
used to, way back, even PMX project in Gulf of Mexico, we used to calculate aging factor based on shear wave velocity measurements. So,
Next time.
yeah.
Thank you.
Okay, thank you. Any other question from the audience? Okay, so thank you,
Thank you.
Dr. Parthasarathy, for your wonderful lecture.
Thank you.
So what is this? You have to hand over the memento. We have now contributed presentations. We have 8 presentations. I know how many are there. First one? Okay. So we'll move on to the second presentation, use of geotechnical techniques to control the high water seepage along the river. Mr. Binay Kumar Pandey and all. Please. So presentation time will be around 10 minutes.
Fine.
Please stick to the time.
Good afternoon all. This is normally a case study we have faced in one hydro projects in Odisha. In this case study, main problem is water seepage along with it's now okay. Yeah. In this small hydro projects, there is some challenges in geotechnical water seepage itself. Along with it, there is some problem in we normally face some problem for the consultant itself sometime, and we have almost controlled the water seepage, but after some time I'll show you in the presentation. This is this hydro project was in Odisha, in Chhattisgarh, Odisha and Chhattisgarh border. There was surface water powerhouse, and for generating the 5.5 megawatt electric. It is simply this hydro project is simply situated at the same river. It's coming from this and going this, means it's forming the forming the curve, and one side is dam side, and it's open channel headrest canal, and after that there was a powerhouse. In the powerhouse area, there was a the consultant has selected the site for powerhouse that was a deep gauge in this area, means river already taking turn at that point, and river naturally there have naturally formed one big pond that is 35 meter long, 25 meter wide and 15 meter deep. This area belongs to geology. This area belongs to Archean and Proterozoic formation. Purple shell and limestone formation is there. This is the geological section prepared by our team. Top 2-3 meter is overburden. After that, shell and limestone embedded, and below after that siltstone and shell. And second L section I have prepared. We have taken some measuring data from putting some chemicals, color at the river body, and we get how where the water is coming at the powerhouse area. Actually, before starting the grouting work, cement grouting work, we have observed taken the Logan value, which is very high, about 175 value, and based on the technical technical suggestion, we have started the grouting, but it would be very difficult to control the water, because water seepage is about 20,000 liter per hour, and initially we are unable to put even one bag of cement in about 5 to 6 bar pressure itself. Then we increase the pressure and increase the hardness also. So, and finally we achieve we control the water seepage about 2,000 liter per hour. But and this work was going on about 7 to 8 months, and we control this water seepage. We control the water seepage, but at the downstream area there was a filled up material, and client was in hurry to start the construction work, and his consultant has suggested that do the seed pile in that area. Client has deputed another contractor, and they have done seed pile. Due to seed pile, due to high vibration and all these things, all the grouting work was damaged, and due to this, client has again shifted the powerhouse location at the downstream area. This was the conclusion, sir. Thank you, sir.
Thank you for maintaining the time. We can take one question. Any question from the audience? Okay.
Namaskar, sir. I got that your Luzon value you have decreased up to 65. Even 65 is that will be high permeable.
In final, in last June, we decreased it to Logan value up to 20, and some area is still balanced for grouting itself.
Okay.
But due to client and consultant discussion, all the work was damaged.
Yeah. Even 20 is very high, for
Yes,
the
yes.
space in the dam. Okay.
Yes.
That's why.
Thank you.
Okay, thank you. So next presentation, weathering the future climate resilient road design lessons from Nepal's BP highway flood 2024. Ranjan KC et al. Rajan KC.
Hello, namaste everyone. Good afternoon, respected chairs and colleagues. I'm Rajan KC from Nepal. So I'll be presenting Weathering the Future Climate Resilient Road Design Lessons from Nepal's BP Highway Flood 2024. So I would say it's not a hardcore research study in the conventional sense, but rather an effort toward the scientific documentation of how natural hazards impact our infrastructure, and how such forensic insights can inform future research, design, innovation, and resilient development planning. So this is my table of contents of this presentation. So talking about the event, in last year, September, end of September, there was an extreme event happened in Nepal in 20th September 2024. Nepal experienced one of the most destructive flood events in recent history, a 3-day extreme rainfall event intensified by anthropogenic warming. So the total economic losses reached around 46 billion, with physical infrastructure accounting for almost 39 billion rupees of losses, and over 5,900 houses, 41 highways, and dozens of hydropower and irrigation projects were affected. So these are some pictures and the affected some of the highways. So the most notable one was BP Highway. So that was constructed with the aid of Japanese government, and so the loss was around 9.66 billion rupees for the BP Highway alone, and many other major corridors like Araniko Highway, Puspalal, Kanti, Koshi were severely damaged. You can see also the images here. So these two pictures are from the same highway, BP Highway, so during and just after the flood event. So, talking about the damage summary, so of this highway, I will focus on this BP Highway. So this is a strategic link between Kathmandu Valley, the capital city of Nepal, and the eastern Tarai region of the country. So it's spanning 160 kilometers. It traverses fragile schistose and phyllitic formations with around 114 breezes and 114 breezes. And so during the 2024 event, an extreme rainfall caused landslides, abutment scouring, roadway collapse. So this is the summary. I will go deep down. So this was the methodology. So we did the reconnaissance survey, some of the drone photographic surveys, and some hydrological and meteorological analysis. And after that, we digged up on the probable causes and the impacts of the damage. So this is the study area map. You can see the most affected section of the highway, 26-kilometer study segment. I will go there. So talking of the highway, so I have shown some of the changes where the most of the damage was occurred. So between 136 to 130, so severe scouring with 200-meter washout near Chaukidara, and some of the debris deposition area, floodplain, aggradation, breeze and road washouts like that. You can see one another picture. So beginning from the upstream, this segment parallels at the left bank of Dapcha Khola at a convex meander. So a 200-meter stretch was entirely washed out. Rockfalls up to 2-meter diameter were recorded. So the temporary backfills have reopened traffic, but the convex alignment amplifies lateral scour, making this ridge unstable without realignment or setback provisions. So this is another section majorly affected. So this is 125 to 120 kilometer Chinese section. Here also we can see the convex bands produce multiple washouts and overtopping on retained field slopes. So temporary divergence exists, but tension cracking and percolation through field indicate ongoing settlement risk. So this also signifies the cyclic vulnerability of retained embankments. So this is another section with damages. You can see I don't want to go in deep here. So talking about the event, we did some hydroclimatic analysis. So talking of rainfall, so Department of Hydrology and Meteorology in Nepal recorded 324 mm in 24 hours at one of the stations nearby Komaltar and 313 mm at Khopasi. So producing a basin average of 267 mm, the highest in last 54 years. The spatial map here shown in the slide illustrates the core precipitation concentration in the highway basin, highway area. So using this Thiessen polygon interpolation, we quantified the spatial heterogeneity and performed a Gumbel EVI analysis, which yielded a 773 year return period for this rainfall magnitude. So here is another analysis. So peak discharge was estimated at 1,251 meter cube per second for the rainfall-based event. So compounding hazards, there's a huge role of sediment behavior in this particular event. So this hydroclimatic geomorphic process interacted in sequence. So this extreme rainfall saturated slopes, triggering landslides, entrained debris, enhanced scour and overtopping, which in turn undermined structural elements. So damage type 1 was slope saturation and landslides that happened in most of the sections. Another was erosion and overtopping phenomena. You can see also in the pictures as well. And other was wall and bridge failures on the highway section. And there were cascading mechanism as well, landslides, river erosion, and induced washout, like that. So this is the damage mapping of the whole section with so convex meanders with sinuosity indices greater than 1.2 correspond to high risk zones.
Complete your presentation.
Yeah,
Time
so
is over.
I'm just concluding here. So translating findings into practice. So so it's time to talk about the resilience. So resilience requires climate adjusted, sediment aware and risk informed designs. So key recommendations from this study was to increase the design discharge by 10 to 20% as per the study using CMIP6 projections, maintain a 50 to 100 meter channel setbacks and avoid curvature radius less than 200 meter, like that. And so conclusion is like this. So BP highway flood exemplifies the interplay of climate-driven hydrologic extremes with geotechnical fragility in Himalayan corridors. So this demands for the shift from deterministic to probabilistic design approach for river corridor-based highways, embedding climatic projections, sediment dynamics, and geomorphic alignment optimization into road engineering. So these are some of the references here. So thanks to my colleagues and authors here.
Thank you.
Presentation. Thank
Mr.
you.
Rajan. So now I know. So one maximum one question. So you can take any question from the audience. I think no questions. So thank you.
Yes, thank you.
So I'll hand over to co-chair.
Okay, so continuing with the session, so now we have our next presentation, Geotechnical Investigations for Wind Turbine Foundation by Saurabh. Saurabh, you have 10 minutes to present.
Okay, good afternoon, everyone. My name is Saurabh Gupta. I want to share experiences of some investigations we've carried out for wind turbines in the Kutch area of India, which is in Gujarat. So we've been reading about this. Actually, wind energy is a new frontier. We've been working for the last 35 years. We went from thermal to nuclear to solar, and nowadays wind is all that people are talking about. And India has a very ambitious target to produce wind energy in the years to come. So one of the most ambitious projects is in this area called Kutch. The wind farm here actually once completed the hybrid, it's a hybrid wind and solar plant. It's will be visible from space. So that's how big it is. The Kutch area, for those of you who are not familiar, this is in Gujarat. In fact, even I didn't know the word Kutch comes from the word tortoise. because the area is, resembles the shell of a tortoise. It's got a hard shell, like a desiccated shell, and then it's soft inside. So that's precisely what it is. It's actually no man's land. If you haven't been there, don't. There's nothing for miles across. If you just stand, you can see like till the horizon. So very tough site for us to work, to carry out investigations. This is beyond the BSF post, actually, near the border of Pakistan. So this is a very simple presentation. We'll just share our experiences or the results of the investigations we've carried out in this area. Again, since it's no man's land, there's very little past experience of investigating the strata in this area. So I think this project gave us an opportunity to really understand the geotechnical properties of the Kutch area. So let's see what we did. In the last 2 years, actually, we've investigated more than 300 wind turbine generator or WTG foundation locations in this area. So usually these are, quite far away from each other. At each WTG location, typically the customer-defined scope was, to do one borehole, one cross-hole seismic test, and then, of course, electrical resistivity test and field CBR. At a few locations, and very much on our insistence, we also carried out some CPTs. So it's interesting, and I've picked one case study, where we've carried out CPTs as well as boreholes, just to illustrate the findings. You see, I was quite happy to find that the CPT-based, soil behavior type actually matched what we get from boreholes quite well. Right, even for these very typical kind of soil conditions. So the Robertson correlations were bang on, which is very encouraging. This is what the stratigraphy basically is. It's 30-70, it's 30% sand, 70% silt. It's actually non-plastic silt. So that's what you get here. In terms of moisture content and liquid limit, the moisture content is almost close to liquid limit. It makes it almost a perfect candidate for liquefaction, actually. It's highly liquefiable soils, as we will see. The cross-hole seismic test results, and we've done so many of these. Again, we did 300 cross-holes, unfortunately without deviation survey. The customer did not take our opinion on this. But nevertheless, the cross-hole results, you see the shear wave velocities are extremely low, typically less than 200 meter per second, down to depth, and fairly consistent across the region as well. We also played around, and again, very encouraging, we compared the N60 values, corrected for energy. We compared the N60 values from boreholes with the empirically correlated N60 values from CPT. That's a plot on the left. So the green dots are the measured or the recorded SPT values, and the black line is the interpreted N60 value from CPT. Fantastic match. And very frankly, this is something which we get across the length and breadth of the Indian subcontinent. So no, it's not just particular for this project. The shear wave velocities also we compared. Again, so you know that the CPT values can be correlated to shear wave velocity, just like SPT. So we compared that correlation with the actual measured shear wave velocity profile from cross-hole, and we got a very good match. I was keen to do seismic CPTs, but the customer was not keen to pay us for it. Which brings me to the next point, and this is not in the paper. I just wanted to discuss. We always believe that the key point in any investigation, any project, is not to copy paste the investigation program, but to think about what are the geotechnical challenges and what's the best way forward, right? So unfortunately here the scope definition came in the form of a BOQ from the customer, and they were not open to change. But really, and this is what we pitched to them. We said that, hey, this doesn't make sense in strata like this. It doesn't make sense, and in terrain like this, difficult terrain, it makes no sense to go and do so many boreholes, lab testing and cross-hole and all that. It's very painful, very time-consuming, very expensive. So we did make a pitch that, okay, for 263 WTG locations, rather than doing borehole-based investigations, we could have just as easily done CPT-based investigations. And we did the math, and we showed them that investigation program 191 days can be completed in 38 days, apple to apple, at a lower cost, and you get much more reliable data, right? So if I was a decision maker, I would have jumped at this, but this didn't fly, right? But now we are doing another project, incidentally, in Kutch, which is a complete CPD-based investigation program with seismic CPDs and CPD samples, and working quite well. I want to quickly touch on the liquefaction analysis. So we checked this out, and this is obviously zone 5, 7.5, 0.36 PGA area as per the Indian code. And we ran, because we had all the three numbers, we ran the liquefaction analysis based on SPT, based on CPT, as well as shear wave velocity, just to see what we get. So this is what we got from SPT. Pretty much everything down to 25 meters investigated. Factor of safety was less than 1. Everything liquefied. We got the same story from shear wave velocity as well. And of course, the same story from CPT as well. The fun part was putting it all together, right? And I've been running these liquefaction analysis for a few years now. To be honest, the CRR values are never matched for me. I don't know what's your experience, but for me, they usually haven't matched. Here, I was pleasantly surprised to find that the CRR profiles from all three approaches matched bang on, right? So this is very surprising, but also very heartening, right? It gave us a lot of confidence in all three approaches and in our final results as well. Of course, we converted this to LPI, and naturally, I mean, the liquefaction potential index of these soils is extremely high. Naturally, the liquefaction is not limited to 25 meters. It's likely going much deeper. We only investigated 25 meters, right? So I want to bring us to conclusions. So obviously, we always push for advanced testing methods as an organization and, you know, in the industry. We also push for customized investigation programs, not copy-paste BOQs. I think it really makes a lot of difference. We saw how different approaches kind of matched each other. The SPT values, N60 values talk to each other, the stratigraphy, the shear wave velocities, the liquefaction analysis, everything kind of matched quite well for these soils. We did recommend that, you know, additional investigation should be carried out to deeper depths. It didn't fly. We did recommend that we go for better testing. Didn't fly. In the end, the customer decided to go for vibro stone columns. These are currently being installed all across. Again, we did push and we did recommend to do before and after CPTs. So that's the other way that CPTs would have been very useful. If you had the data, it could have also been QA/QC for the ground improvement program, but didn't fly. So with that, I end my presentation. Thank you. I'll take questions.
Yeah, thank you very much, Saurabh. Well in time, so we can take one questions from the audience. Someone has any query? Yeah.
Thank you, Saurabh. Nice presentation. I'm Uday Rajneubani from Nepal. I'm just asking you for, with your experience, what is the ratio of 50% CPT or drilling bore wells, or 80-20 or 70-30?
Great question. We get this question a lot, and we actually wrangled with this question for many years when we started doing CPTs. There is no right answer. Okay, it really depends on a combination. Depends on what you're building, where you're building, and your own confidence level. So these are the three deciding factors. So if I was to take two extremes to explain, if I'm building a low-rise structure in an area where I'm very familiar with the geology, with the soil conditions, right? And I have good degree of confidence, I can go 100% CPTs. In fact, nowadays we do that. So for warehouse projects, for low-rise buildings, plotted developments, you know, we go full-on CPTs, okay? So 100-0. On the other hand, if I am working, say, on a tall building in an area where, you know, I haven't worked before, I'm not familiar with the geology, I'm not confident, we kind of, you know, we'll go whatever, 50-50, 30s, whatever. You know, we kind of wing it like that. Sometimes it makes sense to do both, cross-correlate at the site, and then take a decision on the scoping going forward. So it's always best to leave, you know, the investigation programs and the scoping a little flexible, so you can kind of have fun with it. Yeah. I hope that answers your question.
Okay, thank you.
Yes,
thank you. Just one query, Saurabh, I have.
Yes.
Any problem with respect to drilling?
No problem. Why?
In this area of Kutch, you have having
No
drilling
problem
was
at all.
successfully. You are
Very
able
easy.
to.
It's not that bad. It's not like marine clay. It's It's not that bad. It looks worse than it is.
Okay. Okay. Thank you. Okay. Thanks a lot. Okay, now we move on to the next presentation. I think this we have not. I will just announce that presentation: experimental investigation of rock anchor for plate load. Any speaker there? You are there? Okay.
This one is added now.
The presentation you have done? That's why I thought I will. Influence of cavity placement in lateritic rock strata on collapse load, a case study.
A very good afternoon, everyone. I'm Annapurna Sakhardande. I'm pursuing my PhD at Goa College of Engineering, affiliated to Goa University. My topic for today's presentation is influence of cavity placement in lateritic rocky strata on collapse load. It's a case study performed at a site in North Goa. The co-authors for this paper are my PhD guides, Dr. Ganesh and Dr. Nisha. So this is the flow of my presentation. I'll be doing a brief introduction, then speak about the problem that is actually tackled over here, then the input parameters used, analysis, results, and conclusions. All right, so what exactly is laterite and what is its geological classification? Now, we know geological classification, the rocks are classified into metamorphic, igneous, and sedimentary. But that doesn't happen with laterite because laterite is a weathered rock. It is not, it doesn't come, you cannot call it a sedimentary rock, you cannot call it a metamorphic rock, neither a igneous rock. The images that are seen here, the top one you can see is Metagravac. The cursor, okay. The top one you can see is Metagravac, which is the protolith, the parent rock for laterites in Goa. Now, what is Metagravac? It's a metamorphic rock. If you go down, or initially the Metagravacs are sedimentary rocks called gravacs. They get metamorphed into Metagravacs, and Metagravacs get weathered to laterites. Right adjacent to it is the basalt. This is found in West Bengal. And basalt, as we all know, is a igneous rocks. Right at the bottom, you can see sandstone, which is the protolith in Bihar. So you can see all the different types of rocks from all the geological classification get eventually weathered into laterites. Now, what are the problems with laterites in terms of numeric modeling? The first problem, all the numeric models that we have in software assume homogeneity throughout the strata. Now, homogeneity itself is a problem for laterite because we all know in a lateritic quarry, as we go deeper down from the surface, what will happen to the strength? It will go down. Higher up, or higher is the altitude of laterite, higher is the strength. You can see the color of laterite near the surface is reddish, more oxidized. When you go down deeper inside the quarry, it is a little lighter. That lighter color will never give you a better UCS. So that is a basic problem in laterite modeling. Second is unavailability of properties or constants. Now what happens is all the other rocks, there's ample of literature and there are ample of properties which are already published. Of course, they have a range, but the range for laterite is too wide. First and foremost, because a lot of its geochemical properties depend on its protolith, depend on its parent rock. And this wide range, to give you an example, there is a book by M.D. Gedigasu, I think it's published in 1974 by Elsevier Publications. The UCS value ranges from 100 psi to 10,000 psi. Now, in this range, let's say, for example, you get a site and you want to do some kind of work on that site, and you don't have the exact value of UCS. Now, what value are you going to assume? So this is a major problem with laterite. This particular work addresses the fourth problem with laterite, and that is the presence of heterogeneities. Heterogeneities, to be specific, over here I'm talking about cavities. Heterogeneities in laterite are of two types, sinkholes and cavities. Right here also in this Bambolim plateau, there are a lot of cavities which have been encountered in the past. This work is actually carried out at the site in North Goa, Verna Plateau, where there were multiple cavities found. In fact, 2 cavities were found in the exact same vertical plane. So these are some of the sinkholes which are found in Goa in probably last 2 or 3 years. Now, what is the problem that I'm tackling over here? This right at the extreme corner is a site Google map of Google image of the site map, and the schematic of the model that is created using Optum G2. It's academic version software, and this 2D analysis of this cavity was made. What I've tried to simulate is an isolated footing, and under the isolated footing, spherical cavities were analyzed. Diameter of the cavity was kept 2 meters. Why 2 meters? Because the geotechnical investigation of that site indicated that the cavity sizes will not cross 2 meters. And this structure was just a ground floor structure. So isolated footings were proposed by the consultant. So I have taken the axisymmetry condition for a circular footing and carried out the analysis. Effect of lateritic cavities on collapse load were determined using Hoek-Brown criteria. Hoek-Brown model was used because Hoek-Brown is the most suitable model for a discontinuous or fractured rock. And the cavity spacing, when there were multiple cavities in the same vertical plane, the spacing between the cavities was varied from d/4 to d/2 to d. Intact rock strength was varied from 2 MPa, then 3 MPa and 4 MPa. Why so much? Because we were informed that expected strength would be 4 MPa. But then there was nothing mentioned in the geotechnical report, so we went down to 2 MPa to do the analysis. The input parameters used were unit weight was taken as 22 kilonewton per cubic meter, saturated unit weight was taken as 24, the petrographic constant was taken as 5, and geological strength index was taken as 35. Now, why is these values? From the published literature, the expected range of petrographic constant, MI, is 5 to 15. And for geological strength index, it goes from 35 to 75. To keep it conservative, I have taken the lower values. The cavity diameter was taken as 2 meter. Cover depth was taken from 1 meter to 4 meter. Now, all these input parameters do confirm with the published literature, which is telling the properties of the laterites, the global properties. Now, analysis, finite element limit analysis was performed on this particular model. Axisymmetric loading conditions were created. Adaptive meshing was used. Multiplied distributed load with an initial value of 10 kilonewton per square meter was used. Model was taken 4 times the model length was taken 4 times the cavity diameter. Now, why so? Although this is not published in this particular paper, a sensitivity analysis was performed to decide on what should be the depth and what should be the length. And it was noticed from the point of view of accuracy and saving the time, 4 times diameter was sufficient enough. The depth was limited to 20 meters. Why 20 meters? Because I told you homogeneity is assumed over here. If I go too deep, then I cannot, that particular assumption doesn't hold good. Vertical boundaries were restrained against horizontal movement and bottom boundaries were restrained against vertical movement. Now the objectives, what are the outcomes of this particular analysis? The first objective was to determine the effect of lateritic cavities on collapse loads. Influence of intact rock strength and cover depth on the collapse load was also determined. Influence of single and multiple cavities in the same vertical plane was also determined. And the effect of spacing between the cavities on the collapse load was also found out. This is the first result. Now what you can see in the graph, there is a blue, red and black line. Each line is corresponding to the sigma CI, that is the intact rock strength of 2 MPa, 3 MPa and 4 MPa. As expected, lower the intact strength, collapse load expected. On the vertical axis, what is mentioned is collapse multiplier. Collapse multiplier is a factor. So this factor is multiplied to the initial load. I told you initial load taken is 10 kilonewton per meter square. So if the collapse multiplier I'm getting as 10, then my collapse load will be 10 into 10. So this is the multiplier that is plotted against the cover depth. So from this particular plot, it is very clear for lesser cover depths of 1 meter, you can see the expected collapse loads are very, very less. And they go on increasing as the cover depth increases. That is something that is expected. The cavity goes deeper, the collapse load expected is higher. But then till how much? So if the cavity goes deeper than 2 meters, that gain is not much. So the collapse load is going on increasing till 1.75 and 2 meters. Beyond 2 meters, the curves are flattening.
1 minute.
Yes.
You need to complete 1 minute.
In 1 minute? Okay. So the next result, this particular slide is talking about single cavity and double cavities. Now again, these are clusters. The red line that you can see, these are 2 lines. For lower ones are for 2 MPa, middle one is 3 MPa, and the top 2 are for 4 MPa. This is happening for, you can see for 2 MPa and 3 MPa, the lines are overlapping. It means, irrespective of whether there is a single cavity or double cavity, it's not having any much effect on the collapse load. That means for the lower strengths, the collapse loads are not changing even if there are multiple cavities in the same plane. Whereas for the higher strength, 4 MPa, there is a change in the collapse load. Obviously, when there are multiple cavities in a 4 MPa rock, it is showing a decrease in the anticipated collapse load. How much decrease? Around 15% decrease is shown in the 4 MPa rock.
Kindly conclude.
Yes, this is my last result, sir. So over here, basically what I've tried to find out is when I change the spacing between the cavities, what is happening. For higher strength, nothing much is happening. When I change the spacing between the 2 cavities, 2 meter dia cavities, from 0.5 to 2 meter, nothing much is happening for 4 MPa to 3 MPa. Whereas for 2 MPa, you can clearly see there is a difference. The lower 3 cluster of lines, it is showing there is a marginal difference of 5% in the collapse load. So concluding, these are some typical images from the software. You can see the shear plane that is generated is always tangential to the cavity. Conclusions are laterite cavities can reduce values of permissible load. Laterite strata with 1 or 2 cavities in the same vertical plane are investigated to determine the effect of multiplier. Reduction in the collapse load will be anticipated for higher sigma Ci and for larger cover depths. Reductions in collapse load due to reduction in intact strength can also be alarming. Change in the sigma Ci from 4 to 3 MPa showed a decrease of 15 to 35%. While the change from 2 MPa to 3 MPa to 2 MPa showed a decrease from 30 to 50% with depth. Variation in sigma Ci suggested need for higher reliability in the prediction of intact strength. The study also suggested that cover depth increased, there would be a noticeable strength gain. However, cover depth for more than 2 meters do not end up in any strength gain because the curve flattens. The presence of multiple cavities is affected only for 4 MPa rocks, mainly at a depth greater than 2 MPa. This was my conclusion. Before I wind up, I would like to thank the managing organizers for giving me an opportunity to present my work over here. Thank you so much.
Thank you. Thanks a lot. Okay, any query, any question? We can take one. Okay, thank you. Thanks a lot. Okay, moving on now, we'll invite experimental investigation of rock anchors for pile load testing, right?
So, good afternoon, one and all. I am Soil Sheikh from SNR Geotechnics Private Limited. The presenting topic is like experimental investigation of rock anchor for the pile load testings. Starting with the first content, for the stability and for the load bearing capacity the defoundation, particular piles, are the critical consideration for geotechnical engineering. And the pilot testing is widely accepted method to evaluate the axial capacity and performance of piles under various load conditions. As shown in the figures, there are different types of rocks, like permanent anchors or temporary anchors. For the existing buildings, so we can make the temporary anchors. For the permanent passive anchors also, we have make the towers like that. So, however, the conventional pile load test is such as the static load test. For the dynamic test, often face challenges related to the cost, time, and logistic constraints, especially for the larger diameter or the higher capacity of piles. In recent years, like rock anchors have been long effectively used for particularly rock-circuited piles. So this study is focusing on the load transfer mechanism, failure modes, and overall of the performance. The laboratory and field tests were conducted to assess the anchor's pull-out resistance, displacement characteristics, and reliability under different geological conditions. The study highlights key design consideration and practical recommendations for the engineering seeking to implement rock anchors in pilot testing projects. So the components and failure mode of rock anchors, as mentioned, the pre-stressed grouted ground anchors act as a tensioning resisting structural member that is installed and bonded with the soil or rock to describe the tensile load into the ground. So commonly referred as, there is IS 10270 1982, and the bonded length considered on the piles nearby the boreholes UCS value on the rock. So we can make on the design on that. So the typically grouted rock anchors consist of three main components, like anchorage system. There is a free length and the fixed length. And the failure modes of the rock anchors, like a failure of steel wires. So to prevent the steel wires ruptures in pre-stressed anchors, a sufficient numbers of strands must be provided. The conservation factors we have to provide it for the design load, which is to determine the number of strands. For the rock grout bond, and that is to prevent a failure between the rock and ground. So rock and sufficient fixed anchors length must be extended into the computer strata. The design bond state at the rock grout interface is based on the IS 10270 as per the. And for the failure of the steel grout bond, like the design bond stress, which is between the steel and grout, is as per the we can get the from the IS 456. And for the pull-out resistance, so we can refer also for the complete extraction of anchor from the ground. It is by the weight and the self weight of the rock. So overburden must be exceed anchor the capacity with a suitable factor of safety. So for the installation methods for our anchors, so there is one the drilling methods, high tensile strand materials, and the grouting preparations, and stressing of rock anchors. The stressing is carried out by the single or multiple pull stressing jacks. So the strands are locked initially with the 5 to 10% of the capacity to remove the and twist selection strands. As shown in the figure, there is actual photographs of installation of rock. So this first figure shows the drilling process for the rock anchors, and figure B shows the anchors load in rock anchors and the preparation for the grouting and the grouting of rock anchors. Actually, as per the experimental practice, there is a minimum curing period for the grout. So 7 days for the stressing is required for the non-shrink GP2 materials like that. And for the experimental results for the experimental experiences for the rock anchor, actually this is a working pile with the dia of 1.5 meter, and this is design capacity that is a 2160 metric ton with the test load of 3240 metric ton, and there is a reaction load is the 405 metric ton for the highest test load we have done. And this the anchor used for this total length is 42 meters with the 27.5 meter is the free length exceeding the as per the IS 10270, and there is a free length is 14.50 meter. And this test is carried out in Navi Mumbai, Maharashtra, and the reaction anchor was designed based on the test load and the prevailing the soil stratigraphic. So the rock anchor with the different types of rocks. So we have collected the data from overall pan India for the different types of rock types like Navi Mumbai, Chennai, then Odisha, then Karnataka, then Goa, with respect to different UCS types, and make the number of stands and for the particularly pull out resistance for the each roll of anchors. From that, there is a graph between the load versus settlement for pile with rock anchor systems. So the figure shows the indicator rock anchor embedded in high UCS rock consistently exhibited same bond strength and lower displacement under the test load exceeding 3,000 metric ton. So importantly, the study also documents satisfactorily performance in weathered rock formations by adopting the conservative empirical UCS approximations. The anchor also installed in a fresh basalt type, like show as the highest performance due to the higher UCS and minimal weathering, like that. So now concluding on the conclusion, so the report field based result of static pilot with the up to the 4050 ton material reaction among the highest published for the rock anchored reactions. And afterwards that there is a research and document case study also essential support the extent of fixed length, which could in turn and promote the broader adaptation of rock anchors for load testings. And although the design and installation of rock anchors can be challenging, the present study also demonstrates they have offer a viable solution for even for a highest reaction load up to the 450 metric ton, and enhancing the tensile properties of the grout through this use of cement additives, reinforcement or combination of both may improve the bond strength and strand grout interface, so thereby increasing the anchor's ultimate load capacity. These are the references, and thank you. Thank you.
Okay, thanks a lot. Any query, any questions from the audience you have?
Hi, one small doubt. Have you considered the influence zone for the overlap zone of the influence for both the anchors, or how we are calculating the influence zone? The
like
overlap of the influence zones.
Yes, we can make design for the overlaps things also.
So, are you reducing the design strength for this overlap?
Yes.
Is there like you are doing with any software, or how you are assessing the reduction?
Actually, we made on the UCS value based on that. Yeah. So there is no software is used.
Okay then, thank you.
Which, sir?
Length of rock in one slide.
This?
Now you said in Maharashtra you got this length, and
this
you are showed in one slide. I think that slide has
nine.
नहीं go up. नहीं था ना उधर इस साइड था ना.
Okay.
Just hold on.
Okay.
So you have said fixed length is in Navi Mumbai you have got 14.15 basalt rock. Okay. While in completely weathered rock it is 12 meters. I think there is some mismatch in that.
Yes. Actually, sorry for that.
Okay, no problem.
Yeah.
Thank you.
Okay, thank you. Thanks a lot. Okay, moving on to the next paper. We have one paper, standard pronunciation test from practice in Bangladesh. Any speaker available? No. Okay. So moving on to the last one now, design construction of the road embankment using cellular foundation mattress. Yeah.
Where is the papers? Sorry, can you help me with the papers? Where are the papers? Where are the papers? I can't see the folder. Oh, I'm okay. Yeah, the last one. Yeah. Yeah, okay. Good evening all, good afternoon all. Firstly, thank you Geotech Asia on behalf of all the co-authors and myself for allowing this opportunity to present this paper. My name is Mitul Dalwadi. What I'm going to do today, I'm going to present the project we did as a lead engineer, what I did. Design and construction of a road embankment using a cellular foundations over a very big ground. So in the next 10 slides, I'll take you very quickly about the project brief, engineering challenge, what we did in terms of solutions, design and construction part of the proposals, followed with the performance monitoring and a summary. So what you see here is a drone image. It may give you an idea about the project location. So the project location is in Rob Royston, is an outer side of the Glasgow in the UK. As a part of the construction, a new link road was planned or required in order to connect or to give the connectivity to the new proposed railway stations, and expected about 1,600 new homes. The project is on a brownfield site, so it's an old railway or industrial cutting. The length of the sections where we put the proposals is on about 500 running meter length of the section, where we found very challenging ground, and height varies from almost nil to 4 meter height. So challenge, as every project we find challenges, and this project was no different. This time the challenge was more on the geotechnical side. The ground conditions was very variable. I just tried to do, did kind of a typical cross sections. You can see is a kind of a made ground, glacial till, followed with the sandstone as a reasonable depth in relation to the embankment. The foundations, the water conditions were almost in a made ground or a perch in the peat layers. The peat layers more, we found almost like a 600% in terms of the moisture content. The thickness of the peat varies almost from a 0 or less as 0.7 meter to a 3.5 to 3.7 meter. This non-engineering made ground, variable compactions, the thickness of a peat layer, the location of the peat layer result and expected in the terms of a long-term settlement. The long-term settlement may not be an issue, but the main culprit is, or main issue is a differential settlement, and that will lead to the issues on our rideability quality. So I would say as a serviceability, that was our main target in order to assess the requirement. So the need for the ground, the improvement, everything, the conventional technique was identified. At the end, the client decided, or the consulting engineer decided to go for a deep soil mixing. However, a client, which is a Glasgow City Council, they use these particular solutions, what I call as a cellular mattress foundations, in somewhere in 1990s, to support the very soft silt and industrial waste for almost like 850 meter length. So that successful, the performance paved the way for these particular solutions. I'll just take an opportunity here to explain, because earlier that solution is what I call as a cellular mattress, known as a geocell. But I'm not talking about this geocell. That geocell is what you typically about 150 millimeter high. I'm talking about a cellular mattress. That's what is a cellular mattress is. It is a continuous and open structure. What you feel here, how we place with a multi-axial grid at the base, and then form with a very highly oriented grids in a zigzag fashion. So what you call is a simply word is a diamond pattern, and fill with the stones. Normally the height is between a half a meter to 1 meter, but in this project we have gone up to like a 1.3 meter, and I'll explain what we did in terms of the work. So to order the start, the design, the work, the bearing resistance and other parts, we utilize the British standards to assess using the slip line field for the bearing resistance. However, the need for the foundations, the settlements, everything, we had to use a 3D Plaxis assessment. What you see here is a one particular element from the west side to east side, and a different zones in terms of the ground conditions, where is about 2 to 3 meter, the embankment field, and particularly the stratum or a cellular mattress we did. In terms of the assessment, the construction period was considered as a one month and a 2 months as a holding period prior to be applied. The bound layers means the asphalt layers. We perform a significant number of the assessment, just showing as a one quick shot. So maximum settlements post just after the construction was in range of about 330 millimeter at this particular chainage. For the same area, the post-construction settlements over 40 years is the range of 300 millimeters. So we expect the settlements will range about 650 millimeter. We carry out some sort of a sensitivity assessment between the 1.3 meter height and 1 meter high cellular mattress. What you see here is one of the cross sections showing at the culvert sections, which shows that 1.3 meter reduce in terms of around 12% in terms of the total settlement. However, the benefit we achieve is more than a 20% into the slope of the settlement. The next step for us was to assess the riding quality. So what you see is the last part. We carry out a kind of the curvature from along the length of the sections, utilizing the concept of the vertical accelerations, how it gives the riding comfort to the case, and it founds the target value of a 1.7 in terms of the kilometer range. So what you see here is a series of settlement curvatures along the length of the wall, and we found that from the target value that the proposal was well within the limit. Considering all the assessment, everything, we thought, okay, the 1 meter stratum or like the cellular mattress was okay. However, given the variability, we went for a 1 meter. So just last 2 slides, I'm going to give you idea about the constructions and the performance monitoring. So in terms of the construction, sometimes it looks very tricky. However, I would say from the experience after a couple of days of a construction, it's a simple construction. No specific, the skill or something in terms of toolbox talks or something. It allowed a work in a really adverse weather. What you can see here in a Glasgow, we get like a kind of a snow conditions and everything, but we didn't stop the construction. It allowed utilizing the simple tools and everything. There's no heavy compactions or no heavy the equipments are required. One of the beauty for this, it allows the fill material of the demolition waste, so it resulted in a significant amount as the carbon footprint as well. So in terms of performance monitoring, what we had to do, given the site conditions and everything, client wanted to ensure that if it settles significantly, then we are ready with the contingency measures. So the series of like a hydrostatic gauge, we installed about 7 numbers of hydrostatic gauge and did the settlements and everything. From the experience, what we did on what we observed in this particular site, that the rate of the settlements identified was faster, but then what we have used in our assessment, but then it also is out faster as well. So that's somewhere where the total value is somewhere in the line. However, one particular locations where we found that the settlement actually happened on the one side of the embankment, not on the center. But thanks to the stiffness of a 1.3 meter, that did not result in any significant distortion or no additional cracking part or something.
Kindly conclude.
However, the client wanted to do some more assessments in terms of the monitoring. So after the construction of the asphalt layer, we use the INSAR. This is more a satellite-based monitoring and everything. And after two and a half years of settlements of performance monitoring, the client was satisfied without any further the remedial measures. So that's the concluding slide. What you see here, the projects, I've taken the photograph image in 2020, and I've just taken the earlier in 2025. That shows the performance of the project. So in a brief, The small geocell or and the cellular foundation mattress, what I've said, they are completely different in terms of the performance. Also, the height gives an idea about the foundation mattress has an influence. It's a proven solution, and at the end of the day, it saved the client for these particular sections almost £500,000 or £500,000 saved to the construction. So in order, it gives the cash carbon in time, so it's a sustainable solution. And I would like to thank the whole team. And I would say collaboration or teamwork definitely is a key to success to all the stakeholders in this project. Thank you.
Thank you. Thanks a lot. Any clarification query you have?
Any difference between computed settlement and the actual settlement?
We identified, there were a couple of locations at the initial stage. We identified that issues. As I said, initially what we observed, the settlement rate was faster than what we assumed, but it is out quickly because the permeability and the variability of ground, what we had to consider, there was certain, so what you call as a slight anomaly or the difference we observed. Yeah. So initial phase. Yeah. So certain sections we have identified there was a less settlement than what we assumed. So definitely, but I would say there was a 20 to 30% as a range from the memory. That was a difference between the calculated and the monitor. But in some sections, it behaves. So I would say that the area where we have considered a less permeability or a less thickness of a peat, because it's quite variable, unfortunately that location has got higher thickness of a peat and it results in a more settlement, somewhere in a less. But in general, because of the stiffness of this particular foundation, we didn't find any distortion. So that is, so there are the locations where there was a difference between two zones, calculated and the performance. Yeah?
Just one simple, very short. Yeah.
No, please. Yeah.
Have you any experience that you used the geocell in slope ground for slope stability?
Sorry, say it again.
Have you any experience geocell are using in the slope ground for the slope stability?
As I said, that the one what I presented is a cellular mattress.
Yeah.
We have used the cellular mattress up to 12 meter, 15 meter high embankments on a very soft soil, something about 100 shear slope at 10 kPa, 15 kPa kind of a things. This particular solution is completely different. Then there are, as I said, the small geocell 150. I would say they are more for erosion control applications. This one is more a structural foundation applications, and that's what we have used. In addition to this, we have also used to support heavy cranes. I myself worked for the projects in Vietnam. That's a load from the crane was in 27,400 kilonewton on 100 shear of marine clay in about 20 kPa. And it performed well. We have done full scale plate load test by a series of an I-beams of a 1.5 meter by 10 meter length, loaded up to 50 to 60 ton per meter square load. But that's more as structural. What I think what you're talking about, the small geocell, that's for more a slope erosion control, not for a structure. Yeah, thank you.
Okay, thank you.
Okay, thanks a lot. Thanks for the interesting. So now coming back to the session, we are almost done with the session. So just briefly summarize that we had a very interesting session this way. Tone set by Dr. Partha Sarathy on a very interesting topic of carbonate, and then we have the speakers from presenting different case studies on different challenges of the soil. And I am thankful to all the speakers to be in time, and we can complete the session in time. Thanks a lot. Thank you very much. I hand over to the...
Am I okay? Yeah, thank you.
Thank you, everyone. And I would like to give a special thanks to the chair and the co-chair. And we have mementos to present. I would ask Dr. Partha Sarathy to first give to Professor Sumanta Haldar. Professor Sumanta Haldar is a professor of civil engineering and presently head of the School of Infrastructure at IIT Bhubaneswar. He earned his PhD from IISc Bangalore and specializes in geotechnical engineering. Next, I would again ask to present over to Dr. Altaf Osmani. He's the head of design and technical expert in underground storage technologies for hydrocarbons, hydrogen, CAES, and carbon dioxide covering unlined rock caverns. Okay, with this, we have come to an end. Thank you very much, everyone.
Thank you. Thanks a lot.
Thank you.
Thank you.